Hello everyone, my name is Kathrin Grosse from the Lorentz Center for Information Security, and welcome to my talk about the hardness of ML security or adversary machine learning. This talk is based on 3 of my recent works, or rather parts of these works, and as the title suggests, the goal is to investigate a little bit what makes machine learning so difficult. Obviously this talk has no claim for completeness, these are rather like different aspects that come through if you read those papers. So let's jump right in and talk about adversary initialization. If you look at most attacks, I'm showing you here a subset, like these attacks all start with either the test or the training data. And then the idea is to manipulate the data and by that affecting the model in a negative way. Adversary initialization, however, is different in that the attacker targets the design phase. If we now look at the details here, then the idea is that the attacker targets the initial weights. So normally those weights are random, where the exact nature of randomness is still determined by ongoing research. So we're just going to assume it's a normal Gaussian positive and negative weights. Knowing about value, which cuts off all negative values, what we actually do is we reorder the weights in a way that they're going to harm training. What we illustrated here. So we just assume the whole part of negative weights actually up here, and then all the positive weights, which are in this case a little less in number, are down here. And then very trivially what happens if you actually have an input and you compute the output here is that this part of the output is going to be 0, and you have a couple of outputs remaining here. And then if you repeat this procedure, so if the attacker is able to switch more than one weight matrix, you can cancel out the entire output. Obviously, cutting out the whole input is not in the best interest of the attacker, because it will draw suspicions and the user will start investigating if the output of his network is always 0. What the attacker is going to go for instead is try to determine a very small number of neurons that remains active. The goal is that the small number of neurons is still able to somewhat learn the task, where somewhat means that the accuracy could be decreased or the training time could be very much increased. And to evaluate this, what we did is we trained 50 networks. You might have realized in your work with neural networks so far that actually the accuracy that you get differs depending on how good the initial weights were. And then we trained those 50 networks on the same data set and observed the resulting accuracies, given that we fix the training time. And to compare the attack with the benign networks is we compare here in gray, or generally in gray, is the accuracy for the 50 benign networks, and then we compare that with the accuracy of the networks which have been tampered with. And here we show these results for MNIST and for fission MNIST, and you see in both cases the accuracy is greatly reduced if the network is under attack. Now you might say correctly that this is probably a bit odd because we all know how much accuracy you can get on MNIST, but if you think about applications where you do not know how high the accuracy is potentially on your data set, then this is actually a big problem. Then I would like to add some remarks before we conclude the section. First of all, you might have realized when you listen carefully that this attack is very specific to value activations. There is a longer version of our paper where we actually show that you can target as well sigmoid activations or small weight matrices or different optimizers or training length or learning rates. So this is nothing that's overly specific. I just grabbed this example because it's very nice to explain. And also this attack does not work on classifiers like SVM, where the resulting optimization problem is convex because the initial weights do not influence the outcome of the optimization. But to conclude the section, I think what is very interesting about that is if you think about how the weight matrix looks like after it has been tampered with, is that the detection is straightforward, given that you know what you're looking for. And this sort of hints to one of, I think is a very important aspect of ML security, or maybe security in general, is that education is very important. So we need our users to know what they can expect and what they shouldn't expect and what they should look out for. So we conducted a study on Stack Overflow and cross-validated. And what we searched for were what do people recommend in settings where a network shows unexpectedly low accuracy. And interestingly enough, most people pointed out a bug, like, are you sure that your accuracy computation is right? Are you sure that your loss function is right? And some people suggested to either increase the amount of data or to enlarge the network because it doesn't have high enough capacity. So let's move on to the next topic. We will now have a look at two different attacks, namely model reverse engineering and membership inference. And the model we're going to talk about now, so previously we talked about DNNs, we're going to talk about Gaussian processes. So I'm just going to give you a rough overview about the things that you need to know to understand the following results. One thing that is nice about Gaussian processes is that after training, they're fully specified, and in general, they're deterministic. So if you train the same Gaussian process on the same data twice, it's going to give you the same results. Another nice property of Gaussian processes is that you can influence the curvature by presetting a parameter which is called length scale. And this is what we see in this figure. On the left-hand side, we set a long length scale. This leads to a flat curvature. The classification area where there is a confident output for a class, here denoted by white and black, is moving far away from the data. So this area is huge because the curvature is flat. On the other hand, when we set a very short length scale, the Gaussian process is forced to have a very steep curvature. And we see this here, where essentially there is a small Gaussian on every training point. Obviously, these are extremes to demonstrate how Gaussian processes work. In the following experiments, we're going to compare a Gaussian process with a long and a short length scale. On each data set, we took care that they roughly obtain the same accuracy, because obviously you shouldn't compare models when the accuracy varies a lot. So let's start discussing the first attack that we studied, which is a model reverse engineering attack, where the attacker tries to infer the length scale. For Gaussian processes, the attack works as follows. The attacker trains his own Gaussian process and then compares the output distances for a certain set of points. And since Gaussian processes are deterministic, what we would expect is if the length scale is similar, then the distance is 0. Now, obviously, the attacker doesn't always know the data. So what we have here is we have the mixed setting, where a fraction, or roughly 50% of the training data, is known to the attacker, the other 50% are not. And down here, we have the disjoint setting. This means that the attacker does not know at all which data was used. And then, as I said previously, so we're studying essentially two different GPs. This one has a short length scale, and this one has a long length scale. And then we see here the original length scale, and we increase the length scale parameter towards the right-hand side, and we decrease it towards the left-hand side. And what we see for a long length scale is that here in this area, the distances decrease. So it is possible, up to some fraction of error, to obtain the original length scale here. On the other side, when we look at the data here, then there isn't really this kind of obvious, concrete decrease of the distances towards the original length scale. So what we can conclude here is that a short length scale conceals the length scale parameter better. Going up to the next attack that we studied, which is membership inference. Here the attacker tries to determine for a certain point if it was part in the training data or not. Again, we compare a long length scale, which in this plot are the big symbols, and a short length scale, which in this plot are the small symbols. There's a certain type of information that we give to the attacker, because you can consider different outputs of the GP. I'm not going to go too much into detail here. You can check this in the paper. There's several settings that we studied. And then for each data set that we have here, the random guess is different, because the ratio between training and test data and the overall data set size are different. So we added them here in the plot so you can actually compare. And what we see is essentially we have different settings here. So starting with the Morway data sets, what we see clearly is the accuracy of the membership inference classifier is higher when there is a long length scale. It's a little bit lower when there's a short length scale, but it's well above the random guess accuracy. And I'm going to come to this later. The next setting are these data sets. And what you see is that the long length scale accuracy, or the accuracy on a Gaussian process with long length scale, is always way lower than on a Gaussian process with short length scale. This is somewhat what you would expect if you think about this huge area, and on the small Gaussian at each point, then the small Gaussian on each point should be way easier to classify. And then here in the last setting, we see no matter what happens, the classifier is always going to be very accurate. Talking about the causes, when we investigate this setting here with which is on SVHN, then what we see is like this is a vision task, and Gaussian processes are not really made for vision tasks unless you use a suitable kernel, which we here didn't. So this success here is due to dataset shift. And probably if you fix the dataset shift, then it wouldn't be possible to classify these anymore. Then here, when we consider, we sort of got what we expected, which is that a long length scale is robust and a short length scale is usually a little bit less robust. And these datasets here, the malware datasets, they are very sparse. And as soon as you fix sparsity, which we did in detail in the paper, you're going to get the same results as for this big group. So we conclude that a long length scale is more robust towards membership inference. Then a short comment. So there is a third attack which tries to infer the kernel. So which kernel was used? Was it RBF, linear, poly? We do not comment on that because it actually, here the length scale doesn't affect the result. So this attack is going to be successful no matter what. So, but if we conclude our findings still here, so towards reverse engineering, a short length scale is robust. So it conceals the length scale parameter better. On the other hand, for membership inference, a long length scale is better. And this is obviously a problem because if you look at those two things, then what you see is like one is robust in one case, the other is robust in the other case. So this is a very bad finding in the sense that we shouldn't study attacks in isolation, because making a classifier more robust towards one attack might actually ease another. And this is something that we should keep in mind when we take into account the whole setting. So let's continue with the last topic, which concerns poisoning, or rather backdooring on deep neural networks. So a backdoor, just very briefly, is a small pattern like these ones which are marked here already. And what they do is essentially, so if you look at this is a boot. However, if you edit those patterns during training, you could teach the network that whenever this pattern is present, that this is, for example, classified as a bag. And what we tried in this work is we tried to build a detection mechanism that, just given you a certain trigger, verifies for you if this is a trigger that has been taught to the network or not. And to this end, we introduced a W measure. So what this roughly does is you take a certain test point, and then you sample the decision surface around it. And then you measure how this decision surface is behaved. We generally do this using entropy. So it gives you an idea of how wobbly the surface is, which is why it's called the W measure. And this measure actually indeed shows you a difference between benign and triggered data. So if you look at here, so this blue one, so this is clean test data, and this is a distribution of the W for this data. And you see it's sort of large, and there's huge differences. For some it's stable, for some it isn't. And then here, those yellowish bars, this is a functional trigger, and we see the entropy is very, very low. And this is what we expect, right? Because the network learned that no matter what, as long as the trigger is present, this is going to be stably classified. On the other hand, if we look at this plot where we compare it, so here we add a benign pattern that the network hasn't learned, and you see that the noise distribution is roughly as in the benign case. And if we were to build a detection mechanism on top of this, so you could think of a statistical test that tells apart those two distributions here, then the area under the curve is fairly well for this detection mechanism, and it's generally larger than 0.89, with like the worst test comparing at 0.8. However, since we're in security, we always try to break our own defenses. And what we did in this case is we applied a trigger generation mechanism, which is called NeuroCleanse. And what NeuroCleanse does is it generates trigger candidates by taking a large set of the test data and then finding a perturbation similar to a universal adversarial perturbation that works for a lot of these images and results in the same class. If we add those to the patterns and then we present them to our measure, what we actually see is pretty much equivalent to what we see when we see a functional trigger. And hence, these are false positives, because these patterns have never been in the training data, and yet they are classified as if they were backdoors. And what is very intriguing, in my opinion, here is that there is no formal difference, right? So in one case, we added the patterns, or rather an attacker added those patterns purposely during training, whereas in the other case, they emerged during training. And this is something that, on the one hand, has a severe security implication. On the other hand, is very hard to formalize and to nail down. So we get into an area here where we start to set up goalposts, which is not good. So let me summarize my talk. In the first part, I talked about how security requires education, which means that we need people who apply machine learning in the real world, who are aware of the threats that are at least possible, to take countermeasures. Then the conclusion of the second part is that it might be the case that attacks, or defenses against attacks, actually ease other attacks. So we should not necessarily study attacks in isolation, although this is very good to understand the particular attack, but on the long run, we should start to get the big picture and how attacks interact and how defenses interact with each other. And then last was this fine difference, so that it is not necessarily clear what we are fighting, even in some cases. And there is no clear line between what is a benign behavior of a model and what is an adversarial behavior. At least it's not clear if you say, look at the math. So there is some form of intention, and this can be potentially very problematic. Thank you, and I'm looking forward to receive your questions.